Okay, so conditional moments as random variables. That is a mouthful. Let's think about what that means. We've gotten pretty comfortable at this point thinking about conditional moments, conditional means, conditional variances. We sort of know the basic idea. When I say I'm looking at the expected value of x conditional on y equals y1, it means I'm just calculating that expected value using the probabilities for x that are all conditional on y1. Okay, so if it's my kind of standard x takes values x1 and x2, that conditional mean is just x1 times the probability of x1 conditional on y1 plus x2 times the probability of x2 conditional on y1. Okay, so whatever we're conditioning on for the expected value, we condition on it for the probabilities, and it's cool. We could do the variances the same way. If we wanted the conditional mean of x conditional on y2, we'd use those probabilities. So that part's good. Here's the slightly different angle here. The different angle is that when we calculate this expected value, it's a number, right? Capital X is a random variable, but once we take its expected value, it's a number. It's been kind of a refrain of mine over the past few lessons. And if I calculate the expected value of x conditional on y2, that's also a number. And what determines whether we have the first number or the second one? Oh, it's random. It's determined by which value of y takes place. Okay. So these conditional moments are functions of the conditioning random variable, and they are themselves random variables. Okay. What that means is, where we're going with this is that we can take the expectation of the conditional mean. We can take the expectation of x conditional on values of y, and we do it just by taking the particular conditional means of x conditional on y1, conditional on y2, and weighting them by the probabilities and adding them up the way we do any other expected value. And this turns out to be super duper useful. So that's where we're going in this lesson. Let's make it a little bit more concrete right now, and let's continue to sort of work with some of the numbers from the City Council School Board election. So I'm going to just write down some numbers that we derived in past lessons. We had the expectation of X, that was the City Council median voter, conditional on school board median voter being at 1, and that expected value was 2.01, and expected value of x conditional on y equals 2. That was the other possible realization for y. That was 2.77. Okay. So we calculated those numbers before, and sometimes we're interested in them in their own right. But here what I'm saying is, well, how likely are we to be in the world where the expectation of x is 207? How likely we are? It's the probability that we're in the world where y equals 1. And how likely are we to be in the world where x equals, where the expected value of x equals 2.77? It's the probability that y equals y2. Okay. So this happens with the same probability that y equals 1, and that was 0.55. And this happens with a probability that y equals 2, and that is 0.45. Okay. I'm going to take a step here that might not quite be necessary here, but it can be helpful other times. If you start feeling like your head swimming with these expectations of expectations, what we're going to by the end of this lesson, or actually by the middle of this lesson, be calling iterated expectations. Sometimes it's easier to just define kind of an intermediate variable. So I'm going to do that right now. Okay, so I'm going to switch to purple. I'm going to say let z be a random variable. And the random variable is going to, in fact, be the expected value of x conditional on y, but we're just going to call it z here. And so z takes values 2.01 and 2.77 with probability 0.55 and 0.45. And just like we could with any other random variable, let's just find that expected value of z, 0.55 times 2.1 plus 0.45 times 2.77. That equals 2.35. Okay, fine. Think about that number. That's kind of a familiar number. We saw that number before. That is actually the same number we got when we just calculated the expected value of x using the marginals. Okay, the expected value of x using 1 times 0.55 plus 4 times 0.45. Got that same answer. Okay. So maybe this is a coincidence, but I'm here to tell you it's not. This is always true. Okay. It's always true that the expectation over y, I'll explain that in a minute, the expectation of x conditional on y just equals the unconditional expected value of x. Okay, and that is indeed called law of iterated expectations. Okay. So this business, this little like kind of subscript y here, what that's reminding us, and people will say it's the expectation over y. It says that when we're taking the expected value of this thing here, we're using the probabilities that come from y, because that's what's going to determine the expectation of the conditional mean here. Okay. So I have this kind of ambivalent relationship with the intuition behind the law of iterated expectations. Sometimes it just seems kind of like amazing and bizarre to me. Other times it seems so obvious, how could it be any other way? Okay, so when I'm in my how can it be any other way mode, the way I'm looking at it is, this is the expected value of what we will think about y when I'm sorry, well, this is the expected value of what we will think about x when we know y, but it's the expected value over y, so we don't know y yet. So of course, it's just what we expect about x. How could it be anything else? Okay, I had to stop and make my camera behave. I hope it learned its lesson. But I was at kind of a point where it might be worth stopping and pausing, because this claim here is sort of this central point of this lesson, that the expectation over y of the expected value of x conditional on y is just the same as the unconditional expectation of x. So let's go ahead and derive that. And as I like to do, we'll use our bivariate random variables. So x takes value little x1 with probability p of little x1, and little x2 is the other value for x. And that's really all we need here. Actually, and we do need that y also just takes two values. That's the random variable we're thinking about here. And let's just write down those two conditional means. Okay, so the expectation of x conditional on y equals y1. I had this on the other page, but we'll write down the two of them together so we can look at both of them. So that is x1 times p x1 conditional on y1 plus x2 times the probability of x2, still conditioning on y1. And similarly, the expected value of x conditional on y equaling y2. That is x1 times the probability of x1. Now we're conditioning on y2 plus x2 times the probability of x2, still conditioning on y2. Okay. And the expected value of x conditional on y is the expected value of x conditional on y equals y1 times the probability of y1 plus the expected value of x conditional on y equals y2 times the probability of y2. Okay, I think those are all fairly uncontroversial things. Just kind of what I was saying at the beginning, we're all pretty comfortable with right now. If I want the conditional mean of x given y1, I use those probabilities. If I want it given y2, I use these probabilities. And if I want to think about this conditional mean as itself a random variable, I can. It takes this value with a probability that comes from the conditioning event, and it takes that value with the probability that, again, comes from the conditioning event. Okay. You might be thinking, you know how the rest of this proof is going to go because we've been doing proofs like this since math camp, right? We're going to substitute expressions for the two conditional means in here, and we're going to rearrange and see what we find. Okay. So this expectation of y of the expectation of x conditional on y is, okay, so let me substitute this in for that. Here is x1 times the probability of x1 conditional on y1 plus x2 times the probability of x2 also conditional on y1, and that whole thing is multiplied by the probability that we're in the y1 world. Okay, so I've just taken this, I've expanded it, and there's my probability here. And now going to the second term here, the expectation of x conditional on y equals y2. Let's do that same substitution. Is p x1 times probability of x1. Now we're conditioning on y2 plus x2 times the probability of x2, still conditioning on y2. And when we get outside here, we're multiplying it again by the probability of y2. Just straightforward substitution here. And I really think you guys could finish it yourselves, but I'll go ahead and I'll do the algebra here. We're gonna distribute these two terms, write the whole thing out, and then we're gonna recombine them and get something really cool. So what this equals is x1 times the probability of x1 conditional on y1 times probability of y1 plus x2 times the probability of x2 conditional on y1 times the probability of y1. So there's that first part here plus x1 times the probability of x1. Now we're conditioning on y2 times the probability that y is y2 plus x2 is the probability of x2 conditional on y2 times the probability of y2. Sorry, I'm writing off the edge of the page here. Things that I don't like when you guys do in your homework, and here I am doing it. So this factor just goes in here. distributed the probabilities. Now let's just recombine. And what would be the good way to recombine? Well, let's put the x1 terms together and the x2 terms together. So that's what we're going to do. So for x1 here, I have the probability of x1 conditional on y1 times the probability of y1 plus, where's my other term with x1? It's here. Okay, so same things conditioning on y2. Probability of x1 conditional on y2 times the probability of y2. Okay, that takes care of my x1 terms. Now I've got my x2 terms. Here's one and here's one. Let's do the same thing for them. So x2 times the probability of x2 conditional on y1, probability y1 plus probability of x2 conditional on y2 times py2, close my braces. Yeah. Okay, fine. Just back to math camp, basic distributive law of real numbers. These are all the outcomes and the probabilities are all real numbers here. But look what's going on here. Look what we have. Probability of x1 conditional on y1 times the probability that happens, plus the probability of x1 conditional on the only other possible value of y times the probability that happens. The law of total probability tells us that this equals the probability of x1 by our old friend, the law of total probability. Divide and conquer rule for probabilities. Another one of those divide and conquer rules. And indeed, the law of iterated expectations is kind of also a divide and conquer rule. And over here, you see it coming, right? This whole thing, the probability of x2 conditional on y1 times the probability of y1, blah, 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 that equals the probability, unconditional probability of x2. Again, by TP as well. And putting that all together, we have x1 times the probability of x1 plus x2 times the probability of x2, and that sure enough is the unconditional expectation of x. So, you know, I always get a kick out of these kinds of little derivations where things get big and long and messy here, and then they get nice and neat and lovely. But the law of iterated expectations is hugely helpful in statistics going forward, being able to look at those conditional means, take their expected values, get the unconditional means. You will be seeing this a lot. And again, as I was saying before, it really does make sense. What we expect to think about x after we learn y has got to be the same as what we expect about x before we know y. It's almost like, how could it be any other way? It's absolutely true. This is another way of finding that it's absolutely true and has more of a sense of why in it. That it's true because of the nature of the expectation operator and how it takes the individual outcomes, the individual probabilities, and combines them. So it combines them in a way that gives this nice simple pattern to iterated expectations.